Alright, so as our example, we're going to solve z cubed minus 3z squared plus 4z minus 12 equals 0. Now you'll notice that this is actually a factorable equation, which is not in general the case, but that makes it super easy for us to verify did we get the right roots at the end. Which there's a funny story about that, but you'll see. Okay, so step one is going to be substitution. I said take w, or take z to be equal to w minus b over 3a. Now b is negative, so this is going to become a plus, and a is just 1, and the 3's are going to cancel out, so that it's just going to be z equal to w plus 1 is our substitution. Let's see if it works out like I said it would. Alright, so w plus 1 cubed minus 3, w plus 1 squared plus 4, w plus 1 minus 12 is 0. So this amounts to w cubed plus 3w squared plus 3w plus 1 minus 3 times w squared plus 2w plus 1 plus 4, w plus 1 minus 12 is 0. Let's see how this works out. W cubed is the only cubed term here, plus 3w squared minus 3w squared. That's exactly what we wanted to cancel. Great. Plus 3w minus 6w is going to be negative 3w, plus 4w is going to be a positive 2w. So plus 2w No, sorry. Sorry, 3w minus 6w is negative 3w plus 4w is plus 1w. So, just w cubed plus w, and then we have 1 minus 3 is negative 2, plus 4 is positive 2, minus 12 is going to be minus 10 equals 0. So this is our new equation to solve. So what do we do now? We have our p here and our q there. So we're going to take w is equal to u plus v and change this into a system involving u and v. How do we do that? We say that we had a system where u cubed plus v cubed equals q, and if you recall I said minus q, so that's going to be equal to 10. And then we had u times v is p over 3, and p is the negative of that, so we have negative 1/3 there. So this is our system that we have to solve somehow. So what we do, of course, is we weaken it. We cube this second equation, get extra solutions, but it'll make it easier. So u cubed plus v cubed is 10, and then we have u cubed times v cubed is equal to negative 1 over 27. Then what we do from here is to solve it like a quadratic. X minus u cubed, x minus v cubed equals 0. So this gives us x squared minus u cubed plus v cubed x plus u cubed times v cubed is 0. My handwriting is terrible right now. So then we get that this is x squared minus 10x plus a negative, so minus 1 over 27 equals 0. So we have our two quadratic solutions as being negative 10 plus or minus the square root, sorry, that's a positive 10, plus or minus the square root of 100 minus 4ac, so plus 4 over 27, all over 2. We can simplify this if we want to 2704 over 27 in there, which is kind of nasty, but I believe that turns out to be 676 times 4. So we can bring the 4 out, and this becomes 5 plus or minus the square root of 676 all over 27. Oof. So these are our two solutions. These are what we get for u cubed and v cubed. And just conventionally, I'm going to set u cubed equal to the positive root and v cubed equal to the negative root. Let me clear a little space. Alright, so I have our logical chain written over here as well as what we have conventionally decided u cubed and v cubed to be. So now all we have to do is find the cube roots and figure out which ones are compatible. So, I suppose u first, we're going to have its possible cube roots to be, for the record, this is a real number, so I'm not going to even worry about the argument of that. Also, this is a real number. You can plug this into a calculator, and it's actually funny what you'll get out. I won't say anything about that now, but they're both real numbers. So, u can be the cube root, and I mean this in the positive real number sense, of 5 plus the square root of 676 all over 27. That's one of the cube roots. Another one is cube root 5 plus 676 over 27 times e to the 2 pi I over 3, right? Our primitive cube root of unity multiplying that. And the third possibility is the positive real cube root of 5 plus root 676 over 27 times e to the 4 pi I over 3, right? Okay, what about v? V has to be equal to the cube root of 5 minus root 676 over 27, cube root of 5 minus times e to the 2 pi I over 3, or cube root of 5 minus root 676 all over 27 times e to the 4 pi I over 3. Alright, so these are our three possibilities for u and v, and we have to figure out which of these work. Now, it's very convenient in the real number case because, so these are our possibilities for u and v, and we need exactly three pairs that work. Now, it's very easy in the real number case, because we can just look at this and say, we need pairs of u and v that multiply to another real number, right? Negative 1/3. So clearly, these two are a pick. These two are going to match up because e to the 2 pi I over 3 times e to the 4 pi I over 3 is going to be equal to e to the 6 pi I over 3 is going to be equal to e to the 2 pi I is equal to 1, right? That's the logic there. And thus the last pairing is going to be those two. All right, so we have our three pairs, and all we have to do now is substitute back. W is equal to u plus v, and then z is equal to w plus 1. That will give us three z solutions to our cubic equation. And they are, z1 is equal to cube root of 5 plus square root of 676 all over 27, plus cube root of 5 minus root 676 all over 27 plus 1. That's going to be our first root. z2 is going to be equal to cube root of 5 plus root 676 over 27 times e to the 2 pi I over 3 plus cube root of 5 minus root 676 all over 27 times e to the 4 pi I over 3 plus 1. And our last solution is going to be cube root of 5 plus root 676 over 27 e to the 4 pi I over 3 plus cube root of 5 minus root 676 all over 27 e to the 2 pi I over 3 plus 1. These are our three solutions to the cubic. Now, I told you it was kind of funny at the end, and things actually work out. Well, this doesn't look like they work out. Those look disgusting. Well, I told you this method always works, and it does. However, it doesn't always give you things in the nicest possible formula. So it turns out, and you can show this by factoring or by plugging these crazy expressions into Wolfram Alpha, that this expression z1 is actually going to be equal to 3. Although I don't know how to show it. I don't really care either, but you know, it matters that it's right. It doesn't matter that it's pretty. Then the second one, I don't want to cover up that plus 1. Second one is going to be 2i. and the last one is going to be negative 2i. How you show that doesn't matter, but those are our three roots and they are correct, and that is how you solve a cubic equation. Much worse than the quadratic formula, I'll tell you that, but it's very clever and very cool. Hope you enjoyed.